and antisymmetric. Further to this, we have seen what do you mean by equivalence class? Equivalence class is a set of all elements which are related with the elements or a particular element in the equivalence relation. So you would be defining the number of equivalence classes which will be equal to the number of elements present in the set on which equivalence relation R has been defined. I hope I am clear. Okay, let me start the presentation. So part for today's session is partition. What do you mean by partition? In the context of equivalence relation, we are now discussing what a partition is. So a partition of a set S is a collection of disjoint non-empty subsets of S in such a way that if we take union of all those disjoint subsets, we will get the original set. In other words, the collection of subsets AI, where I belongs to some L, a positive integers, okay, a set of integers. This will form a partition of S if and only if these three conditions are satisfied. So what is the first condition? Let me choose a marker. Okay. So the very first condition is if we form a partition of a set, it should not be empty. Empty partitions are not possible. Okay. I will not have A of I equal to 5 for any I belonging to set of integers. Okay. If I take intersection of any two partitions, that intersection should be disjoint, meaning they should not be able to share any element as such. A of I intersection A of J will always be phi, wherein I is not equal to J. And if you assume union of all those partitions, it will result in original set S. I hope I am clear. Okay. This will be more clear once we take a couple of examples based on this partition. What do you mean by partition? Okay, first of all, before going for partition, try to understand the concept. It is a collection of disjoint non-empty subsets in such a manner that they will not share anything in between. But if we take union of all of them, they are going to form the original set as such. I hope I'm clear. Okay, let us proceed. Okay. Now the very first example. Before going for the example, we will be using this pi to denote a partition. Okay. So hence onwards, if the symbol pi is used, it is used for denoting a partition. Okay. Let us take a very simple example. Let us say we are having set A having elements 1, 2, 3. Let me define a partition of A like pi1 equal to 1, 2, 3. Can you tell me whether this is a valid partition, whether pi1 is valid partition or not? How to check? We are having a definition. What definition says? It is a collection of disjoint subsets. So this is one subset. Okay, 1. This is another subset. Further to this, if we take intersection of this should be phi. If I take intersection of 1 with intersection of 2, 3, I will get phi. And if I am taking union of these subsets, I will get the original set A. So I will say pi1 is a valid partition of set A. Are you ready? Further to this, we are observing there are two elements of pi1. There are two elements of pi1, namely one is one subset and other subset is 2, 3. So these elements of partition are known as blocks. Are you ready? So first of all, you will define a partition and thereafter you will have the concept of blocks. Okay. So what are these blocks? These are the elements of partition. So for pi1, I am having two blocks. First block is 1 and second block is 2, 3. Let me take other example. Okay. Let me say I am defining something. Let us say we are having pi2. This pi2 is 1, 2, 3. Can you tell me whether this pi2 is a valid partition? Any replies in the chat box whether pi2 is a valid partition? Yes or no, at least no. Okay, it is not a valid partition. Why? Because one is shared in between these two blocks, and as per the definition of partition, there should not be any sharing amongst anything. So this is not a valid partition. Okay. You might be thinking of why we are learning this. You will observe there are certain instances in the computer science field wherein you will require categorization of various elements into different classes or categories, wherein it is mandatory that there should be utmost security in between two or more classes. So that will result in the concept of partitions. We are having a concept known as clustering, the very important concept in the computer science. If you have heard of artificial intelligence, machine learning, so these clustering algorithms are major pillars of these domains. These clustering algorithms will help you to group the elements which are having similar characteristics together. Okay. So if we are learning the concept of partition, it will help you to categorize various elements clearly. So, here it is. In the number theory, okay, let us take another example. If I say number theory, okay, in number theory, I will say let Z denote set of all integers. This is set of all integers, okay, all integers. So I will say all integers, positive as well as negative, okay. If I define E be the set of all even integers, these are even, okay. And let me define capital O as a set of odd integers. Whether this E and O are forming a partition? Absolutely yes, because there will not be any sharing of any even integer with odd integer. These will have disjoint subsets. These are the two disjoint subsets of original set Z, set of all integers. So this is forming a valid partition. Okay. In reality, you could have as many partitions as possible depending on the number of elements present in any given set. I hope I am clear. Okay. Okay. So I think I will open a Jamboard. If it is feasible at your end, okay, you can answer the possible partitions for the given examples. I'll be writing the possible sets on the Jamboard. If it is possible, you can open the Jamboard at your side and let us have the solutions as well from your end on the Jamboard. Okay. So I think for CG you are using Jamboard, and we will be using the Jamboard for okay, for our practical as well if it is possible. Okay, no problem. So let me open my Jamboard. Okay. Some people need access to this file. Okay. I will. Okay. File is on. I think Jamboard is also on. Okay. So what I'm going to do now, okay, I'm going to write the set, and you are going to tell me what are the valid and which are the invalid partitions as such. Okay. So let me choose the pen. Okay. I hope this is visible. Is it? Is it visible? Is it visible? So let us say it is 4, 5, 6. And I'm writing pi1 equal to whether pi1 is valid partition. First question. Whether pi1 is valid? You can say yes or no, okay, on that line. Is it valid? You can access your Jamboard. You can directly write there. If it is not, it is not. Okay, why it is not? Why it is not? It is not because if you take union, you will have only 4 and 5. That is not equal to original set A. Hence, this is not a valid partition. Agreed? Agreed. Okay. So Jamboard number 2. Let me choose the pen. Okay. Let X denote a set. Tell me what are the valid partitions of X. So this you are going to write in this. Okay. Below any one of you can write. Okay. And there could be lot many valid partitions. The only thing is it should satisfy 3 conditions. First condition is the partition element should not be any empty set. Second, if I take intersection of any two disjoint blocks, it should be phi. And third and foremost, the union should result in the original set. Okay. So this is one. And second one you should also solve. Let us say I am defining a set known as, let us say, set P. Capital P is having elements 11, 99, and 55. So you have to deal with this. Okay. So third one is also written. You can cross check. You have to answer. You have to write the valid partitions. Any problems you can reply in the chat box so that I can move on toward the next point if it is creating a problem at your end. Can you write? That is my first question. Can you write on your own in the Jamboard? No? You're saying no? No. Okay. So what should I do? Why this is the case? It is already shared with all those members which are in the meeting. Okay. And how come you are not able to? Yes. I am observing the Sakshi's window. Sakshi Hingani has opened. Open on Jamboard. Okay. So why you are not able to write? I do not understand. Okay. So let me try to share with 2 people. Okay. So I will share so that you will be able to write. Sometimes it may happen. Okay. So I'm going to share students.computer.sc. Okay. Now just check if you are able to write. I have shared now. Because they don't have full access to G Suits. Okay, fine. No problem. No problem. How come only 2 students are able to see? I do not understand. Okay. So I think I have given some permissions to your representatives, but it will not work. Okay, whatever. So let us go back with our original. No problem at all. So for your information, the answer for this, what was the second thing? The answer for this will be, you could have first partition like, okay, for this x equal to p comma q comma r comma x, I can have partition 1 pi 1 as, wherein I will place all the separate elements p comma q comma r comma s. This will be one possibility. Okay, this is one thing. What else I can do? Let me cross check. Okay. Somebody may say that in pi 2 I am going to have only two pairs. One pair will be p comma q and the other pair will be r comma s. Yes, it is possible and it is perfectly fine. Okay, you can have this as well. And for the third example, 11, 99, 55. First partition will be all elements in separate. So we will have first is 11, 99, 55, three blocks. In other partition, I could have a pairing of 11, 99 and the other block with 55. In other case, I could say 11 is one block and 99 comma 55 is the other block, and so on. So I hope the concept of partition is understood very well. Let me clear out the next point. This can be the concept of partition is applicable to the equivalence relation. Just observe this definition carefully. Let R be an equivalence relation on the set S. Then the equivalence classes of R also form a partition of the set S. So whatever equivalence classes that we are defining on the binary relation R, these will in turn form a partition of S. Conversely, if you have been given a partition, you will be able to define equivalent classes as well as equivalence relation such that the sets present in the partition are the equivalence classes. I am quite sure that you will not understand anything unless and until we will cover up examples. Okay. So what is said here? If we have understood the concept of partition, if we are known with the original set A, its partitions, we can easily define equivalence relation. Okay. And if we are aware of equivalence classes, we can define equivalence relation using the concept of this partition. That is what this particular slide is telling you about. Okay. Unless and until the example is considered, you will not be able to understand. Okay. So let me go back. Whether this slide is visible now, whatever I am talking, whether this is visible, at least give me a reply yes or no so that I can continue further. Okay. Whether this is visible? Yes. Thank you. Okay. So, let A equal to A comma B comma C comma D okay. Pi be a partition on A which is having elements like this. A comma B comma C comma D. This is a partition. Okay. What is asked further? Find. Question is find equivalence relation induced by pi and constructor diagram. Okay. Can you define an equivalence relation which is induced by pi? So while defining equivalence relation induced by pi on a set A, we will look for how many blocks are present in pi. I am having 3 blocks. Okay. If I want to define an equivalence relation in the context of pi on set A, it will have all the 3 properties satisfied, which are reflexive, symmetric, and transitive. So how many pairs we can define for A comma B? I can have a first pair like A comma A, this will be the first pair. Then can I relate A with B? Yes, it is fine because they are the members of same block, A comma B, comma. Other pair that I can do. Okay, after this, which other pairs I can write? I can write for B comma B, I guess. Okay, you can write B comma B. Then you can go for, can we write A comma C? Any replies in the chat box? Can we write A comma C? A comma C? No. We cannot write A comma C because A is present in one block and C is present in other block. We can relate elements which are present in the same block with each other. So I think only one pair is remaining. We can have B comma A. Why I'm writing B comma A? Because symmetric property must also be satisfied, okay, for being a equivalence relation. So you will have B comma A. Further to this, we have to relate. Find the pairs which are related with the second block. I am observing second block is C. So I can have only one pair for that block, which is C comma C. Further to this, for D, I would have only one pair again, and that pair is D comma D. So we are going to have these many pairs present in our relation R. Now let us check out whether this forms equivalence relation or not. So you are observing A comma A, B comma B, C comma C, D comma D. So it is reflexive. Further, let us check whether it is symmetric. A comma B, B comma A is present and others are reflexive. So it is symmetric as well. Let us check for transitivity. A to B forms A comma B. A comma B, B comma A forms A comma A, which is present. And you could observe B comma B, B comma A, it is resulting in B comma A, which is also present. Hence, this relation R is reflexive, symmetric, as well as transitive, and thus it is an equivalence relation. So in your examination, you could have such a type of examples for 6 to 8 marks. Okay. They will give you a partition as well as set. You have to find the relation. Are you getting? Okay. So based on this, can you try for the other? I will write the example here. Okay. Let me check out if you are able to solve this accurately. Okay. Let set x is equal to 1 comma 2 comma 1 2 3 and 5 and pi be a partition induced on x. Induced means imposed. Okay. Or it is defined on that particular 1 comma 2. This is one block. Other block is 3 comma 4 comma 5. What is the task? We need to find equivalence relation induced by pi on x. And you should construct a diagram for it as well. Okay. You should be able to construct the diagram as well. So what is the equivalence relation induced? 4 is absent in excess. Good observation. Okay. So that might not be a partition, valid partition if I do not write a 4. So obviously 4 is also present. Sorry if I have mistaken. Okay. So what are the elements? Here you're going to have, you will have 4 and you're going to have 5 as well. Yeah. One one two two three three four four five five 1 2 2 1 4 5 5 4. Somebody has given the answer. I think Prathamesh has given the answer. Okay. 1 1 2 2 3 3 4 4 5 5 1 2 2 1 4 5 5 4. Okay. Okay. Others, what about others? Whether all are getting the same answer? You will relate 1 with 1, 2 with 2, then 1 2 2 1. 3 will be related with only 3, and so will be the case for 4 5 4 4 5 5 4 5 5 4 in reverse. Yes. Good. Let me go back to Notepad so that we will be able to cover up the examples faster. Okay. Where is Notepad? Yeah. So, so it will be faster. Okay. Otherwise, things are getting. What next? Let R be an equivalence relation. I am writing EQ in short. Okay. On A, then A slash R denotes a partition. A slash R denotes a partition induced on A by R, also known as quotient set of A. So they will ask you in examination in the reverse as well. We have seen one category wherein you have been given. Okay, the first category that we have seen, you have been provided with the partition and you are asked to compute the equivalent relation. The other case, they will provide you the equivalent relation and ask you to compute the partition. So you should be ready with both the categories. Okay. So for this category, what will be the question? Question will look like this. Let x equal to a, b, c, d and r be a equivalence relation on x which has elements a comma a comma c, b comma b, d comma d, c comma a. Question is find xr. This is the partition induced by R on X. That is quotient set of X is asked. Let A equal to 11, 44, 55, 99. Let R denote an equivalence relation. Says we are having pairs. I think one pair is remaining. Sorry. Eleven, 11, 11, 99, 99, 11. Further to this, we will be having 44, 55, 55, 44, 44, 44, 55, 55, 99, 99. Can you tell me quickly? Again, in both the cases, you have to find reverse. The partition is asked. Anuraj has given the answer for first. It is A, C, B, D. Okay. Let me check. So how to find partition? We have to look which are the elements that are related with. Okay. So if you have to find this X slash R, you will first of all check. I am observing that A is related with A is related with C. There is no connection of A with other members like B and D. So can I say this is in one block A comma C? I can have a pair AACC, A comma C and C comma A. So A comma C comma A and CC. Okay, what next? B is related with only B. So we are going to have another block of B. In the similar manner, D is related with only D. So we are going to have its another block. So we are going to have 3 blocks. And whether this is a valid partition, let us check. They are not sharing anything. Further, if I take union of this, I will get original set X, A comma B comma C comma D. So this is a valid partition of relation R induced on X by R. Am I clear? Okay. Second one is also given. Okay, what is second? You are telling the answer for second. It is coming as A slash R is equal to 11 is related with 99. So you will have 11 comma 99 comma. In the second case, you are going to have 45 with 55. If this is clear, can you try some odd example? Okay. Now let us take something different apart from this. Okay. Question I think was asked several times in the university exams, which we will be covering now. So let me check out if you are able to write this. Consider W equal to sheet, comma, last, comma, sky, comma, wash, comma, wind, comma, sit. This is the set. The example number, what I don't know, 20 liters. This is the set W. Okay. Let R be an equivalence relation on W defined by first one has the same number of letters. B begins with find partition of W with R. Okay. Let us say this is R1 so that you will be clear. R1 is this and R2 is this. You have to find partition with respect to R1, comma, partition with respect to R2. First of all, try to understand the question. We have been given a set of words and we have to form a relation. How to form a relation? The terms are given. The pairs will be related if they are satisfying the given condition. What is the first condition? The number of letters in every word must be same, and second condition is the words must begin with the same letter. Those will be related. Are you getting the question? Are you getting this question? Yes or no? Whether this question is clear? Yes. Okay, now go ahead. If the question is clear, you can. Any answers? Okay, first of all, before going for the answers, can you tell me what are the elements of R1? Which pairs will we have in R1? R1, tell me the pairs. What is the relation? The words which are being chosen in R1 must have the same number of letters. R1, last, wash, wind, sky, sit, shit. No, no. Prathamesh, you have given the answer for partition. I am asking first R1. You are telling me the answer of W/R1. So partition, yes, partition might be correct. But first of all, let us try to write relation for those who are not getting okay what we are doing exactly. So has the same number of letters. So can I write sheet comma sheet? Yes, I can write, isn't it? Because both will have same number of letters. How many? 5. Okay. Is there any other word which is also having 5 letters? No. So this sheet will be related with itself only. Let us go for second word, last. Last will be related with last. Next, last can be related with any other which is having same number of letters. Yes, last can be related with wash. Last can also be related with wind because they are sharing the number of letters, 4. In the similar manner, I can have wash corresponding with wash. In the similar manner, you could have in the reverse. That means wash will relate with last. Again, wash will relate with wind. That is perfectly fine. Okay. Further to this, let us go for wind. Wind will relate with itself. Then wind can relate with wash. It can further relate with last. Wind can relate with last because they both are sharing the number of letters. Okay. Further, check for sky, sky and sit. I am observing that both are sharing something. Okay. So you could first say sky, sky, sit, comma, sit, then sky, comma, sit, then sit, comma, sky. Any other pairing? I think I have covered almost everything. Let us check out whether this is equivalence relation. Whether it is reflexive? Yes. The element is related with itself. This is related with itself. This is also related with itself. You are getting sky, sky, sit, sit, wind, wind. So it is reflexive. Whether it is symmetric, if we are having a pair last comma wash, we should look for a pair wash comma last and so on. So I think everything is covered. It is symmetric as well. Let us cross check for transitivity. So last comma wind, wind comma wash. I am taking randomly A comma B, B comma C. It should have a pair last comma wash. So do we have a pair last comma wash present? Yes, this pair is present. So indeed, it is satisfying all the three. This R1 is a equivalence relation that is already given. Okay, for your information, we have taken this. And now we have to find the partition. So what is the formula? Look, okay, to whom these elements are related. So I am observing that this one is related with itself only. So this will be a separate block, comma. The last, it is related with wash as well as wind. So you are going to have this partition, comma. Any other partition? You will have a partition in between sit and sky. Am I clear? Am I clear? Yes. R2 is also given. Okay, fine, fine, fine. R2 is what? W of R2, she is saying last, comma, wash, wind, sky, sit, shit. Very nice. Correct. Correct. Correct, correct, correct. Kartiki, you are going wrong. Okay. Kartik, it is wrong. Or correct? Yes, it is correct. Correct. Okay. I have not. Yeah, yeah. Correct. Everyone is correct. Okay. Fine, fine, fine. I think Kartiki, you are supposed to write sit as well in the first block. You have written only 2 words, shit, comma, sky. You must include sit as well. Okay. Are you clear? So what is the second relation given? Begins with the same letter. So now I am not writing R2, I am directly writing partition induced on W by R2. So what it will be? We will have shit related with sit, comma, sky. How come? Because all these words are starting with the same letter S, comma. I will have wash, comma, wind. And there is no word which is starting with L. So I will have the third block last, which will have last. Okay. Is it fine? Is it fine? Yes. Examples. Okay. Next example. Yeah, yeah. If it is fine, let me give you one more example to try. Let me cross check if you are able to. Okay. Otherwise, instead of going to example, let us go for the next point, because you can have practicing of these examples later on. Okay. So there is a concept known as closure of a relation. What it is, let me try to. First concept is reflexive closure. Let R be a binary relation. I am not now saying equivalence. Okay, let R be a binary relation on some set A. Okay, R1 is a reflexive closure of R if defined as, okay, defined as R union defined as, let me write, R1 equal to R union, how should I put that symbol? Okay, where should I put? Can I put here? Yeah, yeah, yeah. I can comfortably put here also. Whiteboard. Yeah. So we could have R1 as a symmetric closure of R, which will have R1 equal to R union delta. So what this delta is? Delta will be the smallest set of pairs which will compose all the reflexive missing relations in the given R. I repeat, the symmetric closure of a binary relation R is defined as R1, wherein you are taking union of delta. This delta represent all the pairs which are missing for becoming a given relation as a reflexive relation. You will understand this. Okay, I will say here delta, that symbol. R1 is a reflexive closure of R defined as R1 equal to R union delta, such that delta as delta will include missing reflexive pairs. This will be the smallest relation. Okay. Let A equal to 1, comma 2, comma 5, comma 7. R be a binary relation on A which has pairs like 1, comma 2, 2, comma 5, 5, comma 7, 1, comma 1, 7, comma 7. So can you tell me what is the reflexive closure of R based on the definition? That will be denoted by R1. Okay, reflexive closure of R. In short, while computing reflexive closure, you need to add all the missing reflexive pairs in the original relation R. No, no, no. You will keep your original relation as it is. Okay. Along with that original relation, you are going to add up the missing pairs. What is the definition? R1 is original R union delta such that delta will include missing reflexive pairs. Are you getting my point? So you're going to have everything, this entire relation as it is. So I will copy paste. Okay, comma. I could observe that pair 1 comma 1 is present, but this R is not reflexive. Why? Because 2 comma 2 and 5 comma 5 are absent. So you are going to add these two pairs. So this will be the smallest relation which is reflexive, known as closure. Are you waiting? Am I clear? Should we proceed? Yes. So on the similar lines, we have first of all seen reflexive closure. In the similar line, we are having another concept known as symmetric closure. So what it is? Again, let me write here. What changes I am doing now? Just observe. Let R be a binary relation on set A. R1 is said to be symmetric closure of R defined as R1 equal to R union. Now I am not writing delta. R union R raised to C. Are you getting? R union R converse such that R converse will cover all the missing pairs, missing symmetric pairs. And in short, you can directly write R union R converse. Okay, no need of writing the further definition. Obviously, because R converse is going to have everything in the reverse. Are you clear with this definition of symmetric closure? Yes? Okay. Yes. So can you tell me what is the symmetric closure of this relation R? We have seen reflexive closure. So what is symmetric closure? So just for understanding, I am writing symmetric closure of R. Okay. Otherwise, everywhere if we are writing R1, it will be confusing. So let me write here reflexive. Reflexive closure of R. Okay. And here symmetric closure of R. So what it is? So originally I am going to have everything in the context of R. So I will copy paste. Okay. And if particular pair is absent, you are going to include it. So first of all, we are looking for 1 comma 2. 2 comma 1 is absent. That will be present in converse. So I am including 2 comma 1. Next, I am including 5 comma 2. Next, I am including 7 comma 5 because those are absent. Okay. Are you waiting? 1 comma 1 itself is a symmetric as well as reflexive. 7 comma 7 itself is symmetric as well as reflexive. Remember that we have been asked to compute only symmetric closure. So we will not be adding 5 comma 5 and 7 comma 5 comma 5 and 2 comma 2. It is not asked. Only this much. Symmetric closure of R. Okay, fine. 2 1 5 2 7 5. You are adding this. Yeah. Correct. How many pairs in total? 3 plus 3 6 plus 3 9. 6. Anything missing from my side? 1 2 3 4 5 6 7 8. I am getting. Which is the missing pair? 3 6 5 7 1 1 7 2 2 5 5 2 2 1. Okay, 5 2. Neha, you have written 5 2 twice. We will have only 8 pairs, not 9. Okay, you can cross check. Okay, now I think almost the time is over. So as the attendance is taking a long time, what we will do for today's session and hence onwards, I'll be giving you range of starting roll number and ending roll number. Within next 2 minutes, you have to say if you are present or absent, okay, with your roll number. That means you will be saying roll number 1 is present, 2 is present, likewise within that range, and others will be keeping quiet. If you are not able to turn on your mic, you can simply type in the chat box that you are present with your name, so that your attendance will be faster, nothing else. Okay. Do not forget about your test, which is scheduled today at 4:30. Okay, so today is 1910. Let me get the attendance sheet. Okay, roll number 1 to 10. 1 to 10. Be quick. 1 present, 8 present, 4 present, 9 present. Okay. 1 to 10. Any other? 1 to 10. 3 present. Okay. Whether roll number 5 is present? No. Okay. 1 is present, 2 is not present, 3 is present, 4 is present. 5 is not given. Bagal Supnil, Borate, Ashish is not present. Boite Ruturaj. Ruturaj Boite? No. Okay, fine. You can leave. Okay, those who have given the attendance. Uh, roll number 11 to 20. 11 to 20. Ruturaj Bhatti is present. Okay, he has came. Okay, no problem. Uh, okay, who is present? 11, 12, 17, 13, 14, 20, 16, 19. Okay, 11, 12, 13. So 11 is present, 12 is for 13, 14, 15. Do we have 15? 15. Roll number 15. Who is 15? Not present. Okay. चव्हाण रोहन, वैष्णवी देवकाते, धोत्रे श्री विनायक. 18 आहे का? Do we have 18? Roll number 18? No. 19 is present. And Swapnil Farande? No. Okay, you can leave. Fine. 21, 22, 23. 22. 23. 24. Okay. 23 is absent. Fine. 25, 26, 27, 28. 6, 7, 8. 29, 30. 31. Okay, 29 Atharva has came. Okay. 32, 33, 34, 35. 31, 32. 33. 34 is present. 33. 36, 37, 38. 35 present. 36. Okay, 36 present. Okay, fine, fine, fine. I know Khandale Rupali is absent. Okay. 39, 40, 41, 42, 43. 39 present. Okay. 40, roll number 40. 40 is absent. Okay. 44 पर्यंत झाले. ठीक आहे. 40, Putturashish. I think I have seen him. Okay, somewhere. 45, 46, 47, 48, 49, 50. 46 present. Okay. 47 present. Roll number 50 present. Okay. 49, 49, 48, 48 absent. 49 absent. 51, 2, 3, 4, 5. 52 present, 53 present, 57 present. Okay. 52. Yes. 52, 3, 4, 5. Not present. Nigade Anuraj present. Nikam Shubham. Shubham Nikam present. Fine. Nimkhede Manish absent. Nisad Ravi absent. Okay. Pansare Shreyas Parkale Yash 60, 61, 63, 64. 61, 63, 4, 5 present. Fine. Okay. And 60? Do we have 60? No. Okay, fine. 68, 69, 70, 68. Okay, 69 present. Pranav Salunke is present. Good. 70 is absent. Sarkale Rameshwari. 71, 2, 3, 4, 5. 2 is present, 1 is present. 3, 73. No. Okay. 75, 76, 77, 8. 76 is present. Okay. 77, 78, 79, 80, 81 present, 82 present, 78 present. Okay. 76. So I think we are not having 75 present. Do we have 76? 76 is present. Okay. 78 and 81, 82. Okay. Rest are absent. Okay. Anyone remaining to mark attendance? Anybody remaining? No, I think I have covered all. So you can leave the lecture. Thank you.